Good morning and welcome to the lecture number 8 of the course Water Resource Systems, Modeling Techniques and Analysis. In the previous lectures, we have been discussing optimization of functions of multiple variables with constraints. That means, we have now entered into the domain of constrained optimization. Specifically in the last lecture, I talked about the Cohen-Tucker conditions, commonly called as the KT conditions, which are necessary conditions for any optimization problem if it has to have a optimal solution. So, we discussed about a general problem of this type: minimize f of x, and x is a vector of decision variables x 1, x 2, etcetera, x n. There are n number of variables subject to g j of x less than or equal to 0. These are the constraints. We have m number of constraints. So, n number of variables and m number of constraints. For such a problem, the KT conditions are the following. So, we have discussed this at length. So, you have n equations corresponding to the first set of conditions, then m number of equations associated with the second set of conditions, lambda j g j equal to 0. We use this n plus m number of equations to solve for x 1, x 2, etcetera, x n, and lambda 1, lambda 2, etcetera, lambda m. So, n plus m equations, we have n plus m number of variables, we solve for the n plus m variables, and associated with each of these sets of solutions that we obtain, we check the conditions g j less than or equal to 0, which is the original set of constraints, and lambda j greater than or equal to 0, which is the sign of the lambda j's. And as I have mentioned, depending on maximization or g j of x greater than or equal to 0, the lambda j's sign will be changing according to which combination we are talking about here. And then we also examined through a numerical example how we actually apply the Cohen-Tucker conditions to obtain the stationary points of an optimization problem. Then we introduced the most important topic of this course, namely the linear programming. Recall that we said if f of x, which is the objective function, is in fact a linear function of the decision variables, and all the constraints g j of x are all linear functions of the decision variables, and then additionally if the decision variables are all non-negative, then it constitutes a general form of a linear programming problem. But the essential requirement for a linear programming problem is that the objective function must be a linear function of the decision variables, and the constraints must be linear functions of the decision variables. Then towards the end of the previous lecture, I just started introducing the graphical method. So, we will continue with the graphical method of solution. Remember, the graphical method of solution is in fact provides us with motivation for the more rigorous algorithmic way of solving the linear programming problem, which is in fact the simplex algorithm, simplex method of solution. So, we will understand the graphical method correctly, although it is a very simple procedure, but the motivation for the simplex algorithm in fact comes from the graphical method that I will be discussing now. So, we will revisit the problem that I just discussed towards the end of the previous lecture, and from that we will go on to explain the complete graphical procedure. So, we started with the example maximize z is equal to 3 x 1 plus 5 x 2 subject to x 1 less than or equal to 4, 2 x 2 less than or equal to 12, 3 x 1 plus 2 x 2 less than or equal to 18. These are the constraints, and then we have the non-negativity of the decision variables x 1 greater than or equal to 0 and x 2 greater than or equal to 0. These are the non-negativity of the decision variables. Recall that or observe that the objective function is a linear function of the decision variables. The decision variables are x 1 and x 2. All the constraints are linear functions of the decision variables x 1 and x 2. So, all of these are linear functions. Additionally, we have the non-negativity of the decision variables x 1 greater than or equal to 0, x 2 greater than or equal to 0. So, because this is a simple problem with only two decision variables, we can demonstrate with a graphical solution here. The fact that x 1 is greater than or equal to 0, x 2 greater than or equal to 0 leads to the solution being in the first quadrant. So, first we look at x 1 greater than or equal to 0 and x 2 greater than or equal to 0, which defines this region. In fact, this is the first quadrant. So, the solution must lie in the first quadrant. Then we look at each of the constraints. Let us say that we look at x 1 is less than or equal to 4. So, this is the constraint that we are looking at. The binding value for this will be x 1 equal to 4. We have x 1 greater than or equal to 0 and x 1 less than or equal to 4. So, we draw a line x 1 equal to 4, which in fact shows the bound for this constraint. So, you cannot have a value x 1 greater than 4. So, you cannot be looking at this region as far as this constraint is concerned. Because x 1 is less than or equal to 4, it also means that we have to look to the left of this constraint, this line x 1 is equal to 4. So, we are looking at to the left of this line. Similarly, we look at the next constraint, which is 2 x 2 is less than or equal to 12 or x 2 is equal to 6 will become the binding line for this. So, you draw a line x 2 is equal to 6 and then you point the arrow downwards to indicate that you want 2 x 2 to be less than or equal to 12. See what happened. These two together have defined a region now, that any point here will violate this constraint 2 x 2 is equal to 12, 2 x 2 less than or equal to 12. So, it violates this constraint and therefore, it will not be feasible. Similarly, any point here will violate the constraint x 1 is less than or equal to 4 and therefore, this will not be a feasible point. So, among these two constraints themselves, we have now identified that you cannot be looking beyond this particular region for a solution. Then we also add the third constraint, namely 3 x 1 plus 2 x 2 is less than or equal to 18. So, you draw a line 3 x 1 plus 2 x 2 equal to 18. How do you draw? You just need 2 points. So, put x 1 is equal to 0, you will get x 2 is equal to 9. So, 0 9 is one of the points. You put x 2 is equal to 0, you will get x 1 is equal to 6. So, 6 0 is another point. So, simply join these 2 points, you will draw the line 3 x 1 plus 2 x 2 is equal to 18. Because you want 3 x 1 plus 2 x 2 to be less than or equal to 18, we look to the left side of this. So, this constraint says that you look to the left side of this. So, in the earlier region that was defined by these two constraints, if you look at any point here now, we are still in that region defined by the earlier two constraints. But if you look at any point here, that will violate this constraint 3 x 1 plus 2 x 2 less than or equal to 18. Therefore, along with this constraint now, we have a new region defined, which can be shown like this. So, this is the region in which all the constraints are satisfied, and this region is called as the feasible region. So, feasible region is a region where any point within that region satisfies all the constraints of the problem. So, these are the three constraints. So, any point you take within this region or on the boundary of this region satisfies all the three constraints. So, in the graphical method, the first step is to identify the feasible region. So, this is the feasible region. What does that mean now? This means that you have virtually infinite number of points. Any point within this is a possible solution to this problem. So, we have infinite number of points which satisfy all these constraints. From among these infinite number of points, we want that particular point or that particular solution which in fact maximizes our objective function, which is z is equal to 3 x 1 plus 5 x 2. So, is at this point, is at this point, is at this point, this point, etc. So, virtually virtually infinite number of solutions exist, and out of those infinite number of points, we want to choose one point which maximizes 3 x 1 plus 5 x 2. To see which is this point, what we then do is we draw a z line. Let us say we put an arbitrary value of z, z is equal to let us say 15, some convenient value of z you choose, and then draw a z line. So, z is equal to 15, which is 3 x 1 plus 5 x 2 is equal to 15. How do I draw this line? I put x 1 is equal to 0, I get x 2 is equal to 3. So, 0, 3 is one line, one point. Then I put x 2 is equal to 0, x 3 is equal to 5, x 1 is equal to 5. So, you get 5 0. So, this is how you draw this line, z is equal to 15. Now, z is equal to 15, you on the line z is equal to 15, there are several points which are lying within the feasible region, and all of these points correspond to a value of z is equal to 15. What is your objective? Your objective is to increase z to the best extent possible. You want the maximum value of z. So, let us say z is equal to 15, I go to z is equal to let us say 18 or 21 and so on. So, I get another line. So, I keep increasing z, the z line moves parallel to itself. As I keep increasing z, it moves parallel to itself in this direction in this particular case. So, z is moving in this direction now. As I increase z, it moves parallel to itself in this direction. I further increase z, it goes here. So, like this I keep on increasing z as long as there is at least one point within this z line which lies within the feasible region or on the boundary of the region, we have a feasible solution possible and we are increasing z. So, we keep on increasing the z until we hit such a point where any further increase in z will make the z line leave the feasible space altogether. So, as I was increasing z, let us say we were here earlier. So, we keep increasing z, the line moves parallel to itself, and then finally, when you reach this point, when z is equal to 36, any further increase in z will make it leave the feasible space. At z is equal to 36, you have exactly one point in contact with the feasible region, and therefore, that is still a feasible point. Any further increase in z will make the z line leave the feasible region, and therefore, there will be no point on the z line which are feasible. By feasible, I mean they satisfy all these conditions, all the constraints, and therefore, this becomes the last point. Z is equal to 36 is in fact the optimal solution, because any further increase in z is not possible without violating at least one of the constraints, and therefore, it becomes infeasible, and therefore, z is equal to 36 becomes the optimal point. So, this is what we do in the graphical procedure. First, you identify the feasible region. The feasible region is a region obtained by intersection of all these constraints, and then it should also satisfy the non-negativity conditions, and therefore, it lies in the first quadrant. So, we identified the feasible region. Then you draw an arbitrary z line and then start increasing the z, because you are looking at the maximum value of z. If you are looking at minimization of z, then it will be moving in the other direction. So, you have to look at smaller value of z. So, because you are looking at the maximization of z, you would like to achieve as high a value of z as possible, yet at the same time maintaining all these constraints, satisfying all these constraints, and therefore, you are looking for a feasible solution which is also leads to a maximum value of z. And therefore, you move the z line parallel to itself, keep increasing the value of z until you hit a point where the z line is just in touch with the feasible region at one point, beyond which no further increase in the value of z is possible without violating at least one of these constraints, because you will leave the feasible region. The moment you cross this point, you will leave the feasible region, and therefore, this becomes a optimal solution. So, z is equal to 36 becomes optimal solution, x 1 is equal to 2 and x 2 is equal to 6 is the optimal point. How did we get this x 1 is equal to 2, x 2 is equal to 6? You look at this. This point is at the intersection of this constraint, namely 2 x 2 is equal to 12 and this constraint which is 3 x 1 plus 2 x 2 is equal to 18. So, solve for those, you will get 2 and 6 as the solution. So, you obtain the point 2 6 and you got the associated value of z is equal to 36. Verify that 3 x 1 plus 5 x 2 with x 1 is equal to 2 and x 2 is equal to 6 in fact leads to z is equal to 36. So, this is how we solve a problem with graphical method. Identify the feasible region, look at the z line and then identify the point at which the optimal solution occurs. Now, let us look at your objective function here was z is equal to 3 x 1 plus 5 x 2 and you were maximizing this. So, we are looking at in this example maximize z is equal to 3 x 1 plus 5 x 2 and you obtain this z which was moving parallel to itself and therefore, finally, it touched this particular point. Let us say I change the objective function retaining all the constraints and the non-negativity conditions the same. Instead of saying 3 x 1 plus 5 x 2, I will make it 3 x 1 plus 2 x 2. So, let us look at maximize z is equal to 3 x 1 plus 2 x 2 instead of 3 x 1 plus 5 x 2. Retain all the conditions the same, which means that your feasible region still remains the same, because you have not changed the constraints and therefore, the feasible region remains the same. What did I do in this? By changing 3 x 1 plus 5 x 2 to 3 x 1 plus 2 x 2, I changed the slope of the z line. So, z line, the inclination of the z line changes and therefore, the z line becomes this now. Instead of this, the z line now changes the slope and then it starts moving parallel to itself in this direction. At the last point of contact with the feasible region, the z line will coincide with 3 x 1 plus 2 x 2 is equal to 18. I have 3 x 1 plus 2 x 2 as the objective function. So, it just coincides with 3 x 1 plus 2 x 2 is equal to 18. Any further increase in z line will make it leave the feasible space and therefore, this becomes the optimal solution. See that in the previous case we got exactly one point in which the z line was in touch with the feasible space, whereas here it is coinciding with the boundary of the feasible region, coinciding with one of the boundaries of the feasible region. And therefore, any point on this line here, this yellow line here is a optimal solution, which means you do not have one optimal solution, but multiple optimal solutions. In fact, infinite number of optimal solutions all along this yellow line, each of which leads to the same value of z, which is 18, z is equal to 18. So, this case will lead to multiple solutions. So, you need not have one solution, you may have multiple solutions to a LP problem, and the multiple solutions occur when the z line corresponds to one of the boundaries of the feasible region. the multiple solutions offer an infinite flexibility in decision making, because you have the maximized value z corresponding to 18, but you do not have one point, but you have infinite number of points, all of which will lead to z is equal to 18, which is the optimal solution, and therefore, you can choose any of these infinite number of points for your decision. And therefore, we must be alert to the situation that certain problems lead to multiple solutions, and we should be able to capture the multiple solutions. In fact, we will see if you get one solution here and maybe another solution at this point, you should be able to generate all the infinite number of solutions, all of which, remember, will lead to the same optimal solution z is equal to 18. So, this is the first special case that we consider. You identified the feasible region and then saw that z line corresponds to one of the boundaries beyond which it leaves the feasible space, and therefore, that becomes the optimal solution, and therefore, you do not have one solution, but you have infinite number of solutions. All of these points here on the boundary become an optimal solution, lead to an optimal solution, and therefore, you have multiple solutions. If you have two solutions, you have infinite number of solutions. This is a solution, this is a solution, therefore, any point in between is a solution, is a optimal solution. So, you have multiple optimal solutions. Okay. Another special case is that your constraints may be such that you do not have a bounded region. In this particular case, what happened? You have, let us look at this, you have a region which is bounded in all the directions. So, you have a bounded region. Let us say that some of the constraints are such that you do not have a region which is bounded. Let us say your constraint set is such that one constraint is saying you look at this direction, another is saying you look at this direction, and therefore, anything in this region is a feasible solution, and there is, and z line is increasing in this direction. Let us say z is increasing in this direction. So, z can be increased until infinity without violating any constraints, and therefore, the region is unbounded. The feasible space or the feasible region becomes unbounded, and such solutions are unbounded solutions. In general, when you have an unbounded solution, the problem is ill formulated, because obviously, any physical problem you cannot have you cannot increase the objective function value to infinity if it is a well formulated problem. And therefore, when you get an unbounded solution, the problem is ill formulated problem. Typically, you will have another constraint which will limit the increase in the objective function. So, you saw multiple solutions, you saw an unbounded solution. Your set of constraints may be such that you may not get a feasible space at all or feasible region at all. You may have several constraints, and then you are plotting the constraints, set of constraints. Some constraints will define some region, some constraints will define yet another region. There is no intersecting point at all, intersecting region at all. Such problems lead to what are called as infeasible solutions or infeasible problems. So, you may have a constraint which says you look at this direction, another constraint which says you look at this direction, which means that to satisfy this constraint you should be in this region, to satisfy this constraint you should be in this region. Therefore, there is no region where you can satisfy both of these simultaneously, and therefore, there is no feasible space possible. Such problems are called as infeasible problems, or the solutions are infeasible. Another case where you may have some intersection possible with certain constraints, some other intersection possible with certain other sets of constraints, yet together they do not form a common intersecting region. Such problems also lead to infeasibility. In general, when you have infeasible solutions, it means again that some of the constraints that you have formulated are inconsistent with other constraints. and therefore, you need to look at the physical problem and see whether the constraints have been correctly formulated associated with the physical problems. There may be yet another case where you may have a good region of intersection among all the constraints, but this region may not lie in the first quadrant, and therefore, it violates the region violates the requirement of non-negativity of the variables, and therefore, still it becomes infeasible. So, infeasibility will indicate that at least certain constraints are violated or the non-negativity condition is violated. So, in this case, although the constraints form an intersecting region, the region violates non-negativity conditions, and therefore, it becomes infeasible. So, in the graphical method, we have now identified 3 special cases, and in fact, these 3 special cases pertain to any LP problem, not necessarily because we are solving it using the graphical method. The first one is that you may have multiple solutions when the z line is just coinciding with one of the boundaries of the feasible regions, and therefore, any point on this boundary becomes an optimal solution. Therefore, you have infinitely many solutions, infinitely many optimal solutions, all leading to the same optimal value of the objective function. These are multiple solutions. Then you have the case where you may not have a bounded feasible region. So, z can be increased up to infinity, ad infinitum. You keep on increasing z, it does not violate any of the constraints, and therefore, it is still feasible. So, you can increase the z value to infinity without leaving the feasible space, which means that the feasible space is unbounded in the direction in which the z is increasing for a maximization problem. And therefore, it becomes an unbounded solution. In general, whenever you have an unbounded solution, you will have to look at the problem formulation. The problem formulation will be wrong. Then you have the case of infeasible solutions, where the set of constraints is such that you will not be able to identify a intersecting region which also satisfies the non-negativity conditions, which means there is no point in the region of interest which satisfies all the constraints, and therefore, the problem becomes infeasible. In general, infeasible problems are also ill formulated problems, because you may have introduced inadvertently certain constraints which violate other constraints, in the sense that if you meet this particular constraint, the other constraints are not satisfied, and therefore, the problems are ill formulated. We must be able to capture all these situations, that is multiple solutions. We must know how to capture the multiple solutions. We must know when the problem is unbounded. We must be able to identify when the problem is unbounded, and we must be able to identify infeasible solutions. As you saw, this was a simple problem with only 2 variables and 2 constraints and so on. So, it was easy for us to identify. In practical problems, you will have hundreds and thousands of variables and thousands of constraints. Therefore, we must have a mechanism to identify each of these different types of solutions, which we will presently see. So, from the graphical solution, then we must be able to move to higher size of the problems of the LP problems, and therefore, we must have an algebraic way of solution of these LP problems. So, let us start introducing an algebraic method of solution, which is also an algorithmic method of solution, which is called as the simplex method. To do that, we will look at the general structure of the problem, LP problem. We typically write the objective function as maximize z, and z is a linear function of the decision variables. The decision variables are x 1, x 2, etcetera, x n, and z is a linear function of x 1, x 2, etcetera, x n. Then you have a set of constraints, m number of constraints. In the general form of a LP, we write them as equality constraints. So, A11 x1, A12 x2 etcetera, A1n xn is equal to B1. This is for the first constraint. So, the right hand side values are denoted as B1, B2 etcetera, Bm. A11, A12, A13, A1n etcetera, these are the coefficients of the decision variables in the constraints. So, this is the first constraint and the coefficient for the first constraint first variable is A11, first constraint second variable is A12, first constraint nth variable is A1n, that is a coefficient is A1n. Like this you have A21, A22 etcetera, A2n. So, you have a coefficient matrix, we will write in the matrix form subsequently in some other lectures, but you can identify that these are in fact the coefficients which are constants, and x1, x2 etcetera, xn are the decision variables for which solutions are sought. B1, B2 etcetera are the right hand sides of the constraints, these are also known values. Additionally, you have the non-negativity conditions x1, x2 etcetera must be greater than or equal to 0. So, this is the way we write one general form of LP in which all the constraints can be expressed as equality constraints, and we typically look at maximize value of z. This is one general form. You can also write it in another form. For example, you may look at minimization and then still you can retain less than or equal to and so on. But we will stick to one general form and then see how we develop the simplex algorithm corresponding to this general form. Which means your objective function must be of the type maximization. So, we write this in a more compact form as maximize z subject to all this set of constraints. I will write it as a summation in the summation form. You have a I j x j is equal to b I, which means the ith constraint I will write as summation j is equal to 1 to n. There are n number of variables, a I j x j is equal to b I and I is equal to 1 to etcetera m. So, I am writing this set of constraints here in a compact form using the summation notation, and x j greater than or equal to 0, j is equal to 1 to n. There are n number of variables, m number of constraints. Constraints I am denoting it as by I and the variable by j here. So, this is a compact form of LP, still in the scalar notation. So, we write this in the scalar notation as shown here. Now, let us look at various features of such a problem. You have n number of variables and m number of constraints and m number of equations actually, because we have made all the constraints to be equality constraints. We will see how to handle the inequality constraints later on, but in the general form we are expressing all the constraints to be equality constraints, which means what? You have m number of equations and n number of variables. If m is greater than n, that means the number of equations is more than the number of variables, then the generally problem is over defined, and therefore, you should be able to identify redundant constraints, which I have introduced earlier. So, there must be m minus n number of redundant constraints, which you must be able to identify and eliminate. So, that you will have a maximum of m number of m is equal to n number of constraints. So, if your original number of constraints is more than the number of variables, it indicates that there are certain redundant constraints. We must be able to identify the redundant constraints and eliminate the redundant constraints. Then the next question, if m is equal to n, that means your original set of equations is in fact equal to the number of variables. Then you may have a unique solution. That means, if there is a solution, you have now m number of equality constraints, which means m number of equations. You solve m number of equations simultaneously, you will get a unique solution. So, if you have a solution, it may be a unique solution which means that there is no question of optimization, because you have exactly one solution for all the m number of equations, or you may not have a solution at all. So, you may have m number of equations which may not have a solution at all. If you have a solution, it will be a unique solution. Therefore, m is equal to n is not a case to be considered, because there is no question of optimization. So, the only condition that we need to consider is where m is less than n, which means the number of equations that you have is less than the number of variables, in which case you may have infinite number of possibilities, out of which you would look at that particular problem where that particular solution which leads to an optimal solution. So, this is the case that we will be talking about. If m is less than 1, it corresponds to an underdetermined set of linear equations, which means that if there is one solution, then there are infinite number of solutions possible, and out of these infinite number of solutions, we need to look at that particular solution which also maximizes or optimizes the objective function. So, this is the case that we will be interested in the linear programming problem. Okay, which means in the general form, the way we stated, we said the objective function is of maximization type. We will stick to that as a standard form. We will retain the objective function as maximization type. Then all the constraints are of equality type, and all the decision variables are non-negative. If you have any optimization problem, then we should be able to express that optimization problem which satisfies these three conditions, which means that you may have a minimization objective function as minimization. You must be able to express it as a maximization problem, and you may have certain constraints or most of the constraints as inequality type. Some of them may be less than or equal to, some of them may be greater than or equal to, and some others may be equality type, which we should be able to express all these constraints as equality type. Then we must also be able to express all the variables as non-negative. Let us see how we do this. If you have the objective function as minimization, let us say that your objective function is minimize j is equal to 1 to n c j x j. These may be cost coefficients and there are n number of variables. I am only writing the objective function here. The objective function is of the minimization type. This can be written as maximize minus c j x j, summation j is equal to 1 to n. As you recall, in one of the earlier lectures I had shown that if you want to maximize f of x, it is the same thing as minimizing minus f of x. So, simply take minus c j x j and maximize that. So, a minimization objective function can be written as maximization objective function by simply taking the negative of the function itself. Then the second one is, if you have less than or equal to constraints, we need for our general form equality constraints, but our constraint may be of this form. At the kth constraint, let us say a k 1 x 1, a k 2 x 2 etcetera, a k n x n less than or equal to b n. This is the kth constraint. Let us say that I want to convert this into equality constraint. Now, the left hand side is less than the right hand side, and I want it to be equal to, which means what? I have to add certain value here, certain non-negative value to the left hand side. That is what we do. We add an additional variable here. There were n variables in the initial constraint. We add another non-negative variable x n plus 1 to make it equal to b k, and this additional variable is called as a slack variable. There was a slack that was existing, you fill up the slack with the slack variable. So, the inequality constraint of the type less than or equal to, we convert it into an equality constraint by adding a non-negative variable, and this non-negative variable is called as a slack variable, and this non-negative variable will be this slack variable will be non-negative. So, x n plus 1 which you added, which was not there in the original problem, but you added an additional variable, and that is called as the slack variable. that is x n plus 1, and that will be non-negative. Similarly, if you have a greater than or equal to constraint, let us say we will just look at a small example here, 3 x 1 plus 2 x 2 less than or equal to 18, which means what? Your left hand side is less than 18 and you want to make it equal to 18 by adding one non-negative variable. So, I will write 3 x 1 plus 2 x 2 plus x 3 is equal to 18, and this is called as the slack variable. And your x 1 and x 2 are anyway greater than or equal to 0, the additional variable that you are adding is also greater than or equal to 0. So, you are satisfying the non-negativity condition. Let us say you have an equality constraint instead of the you have a greater than or equal to constraint instead of the less than or equal to constraint, which means what? The left hand side is more than the right hand side and you want to make it equal, and therefore, you should deduct some value from that, and therefore, you subtract a non-negative variable from that. So, a k 1 x 1 etcetera minus x n plus 1. So, you add another variable with a negative sign now in the constraint. So, the variable is non-negative, but you will deduct from the left hand side of that, and this is called as a surplus variable. There was a surplus on the left hand side, you are reducing that by deducting a surplus variable, and this surplus variable is also non-negative. So, if you have a less than or equal to constraint, you add a non-negative value, non-negative variable, that is called as a slack variable. If you have a greater than or equal to constraint, you deduct a variable, deduct a certain value using a surplus variable, and both the slack variables and the surplus variables that you so introduced were not there in the original problem, and you introduce them to make sure that the constraints are expressed as equality constraints, and both the slack variable as well as the surplus variables are non-negative. Okay. So, if you have let us say x 1 plus x 2 greater than or equal to 5 as your original constraints, you will put x 1 plus x 2 minus x 4 is equal to 5, and this x 4 is in fact the surplus variable. And the surplus variable is also non-negative, you will get greater than or equal to 0. X 4 greater than or equal to 0. Then the last requirement is that all the decision variables must be non-negative. So, we looked at the objective function, we wanted objective function to be maximization. So, if your objective function is minimization, you can convert it into maximization by looking at minus f of x. If you are looking at minimize f of x, you can look at maximize minus f of x. Then you wanted all the constraints to be of equality type. We just now saw how to change the less than or equal to type of constraints to equal to constraints by adding what are called as the slack variables, which are non-negative. Then if you have greater than or equal to type of constraints, you deduct a surplus variable, which is also non-negative. Then the third case is when you have certain variables which can also assume negative values. Remember, in most of the engineering decision making problems, the variables that we will be talking about are either physical variables. For example, we may be talking about dimensions, physical dimensions of flood control storage. You may be talking about the amount of hydropower that is generated, amount of water that is applied to a particular given to a particular city, and so on. So, these are physical variables that we will be talking about, and most of the cases they are non-negative. We will not be talking about negative variables. However, there will be certain cases where you may have to account for variables that are unrestricted in sign. For example, you may be talking about temperature. Temperature can assume negative values. And in such situations, there must be a way of handling these variables in the general linear programming problem. When you have a variable which is unrestricted in sign, which can assume negative values also, it can take positive values, it can also take negative values. In such situations, you must be able to convert that for the problem formulation into a non-negative variable, not the original variable itself, but we will convert, we will use those variables which are all non-negative. How do we do this? Let us say you have a variable x which is unrestricted in sign, which means that in the problem solution it can assume negative values also. If we express this x as a difference of two non-negative variables, let us say that I will put x is equal to x 1 prime minus x 2 prime, and the x 1 prime and x 2 prime will go as decision variables. So, x 1 prime and x 2 prime can be non-negative. So, that if x is negative, then x 2 prime will be greater than x 1 prime. Let us look at it more formally. So, an unrestricted variable can be written as the difference of two non-negative variables. Let us say that you have x I is unrestricted in sign, then we can replace x I by a difference x I 1 minus x I 2. So, I will write x I as x I 1 minus x I 2 with both x I 1 and x I 2 non-negative. So, if in your final solution x I has to be negative, what happens? X I 2 will be greater than x I 1, and if x I has to be positive, x I 1 will be greater than or equal to x I 2. In fact, in the solutions you will see that only one of them will be non-zero. However, we will come to that later, but right now you just understand that you by expressing x I as a difference of two variables, two non-negative variables, what we have achieved is that in the final solution, if x I has to be positive, then this will be more than this. If x I has to be negative, then this will be more than this, both of them being non-negative, and therefore, in the LP problem we will still be dealing with non-negative variables. So, you are able to convert the objective function into a maximization type, you are able to convert the less than or equal to into equality constraint, greater than or equal to constraint into equality constraint, and you are able to convert the unrestricted variables into non-negative variables, and therefore, any given problem any given LP problem can be expressed in the general form, which requires the objective function to be maximization type, which requires all the constraints to be of equality type constraints, and which requires that all the variables in the LP problem are non-negative. So, this is how we achieve that and then express a given LP problem in the general form. Now, with this we will start introducing the algebraic solution, which is a simplex method. Now, I repeat this many times that you can do away without knowing the way the algorithm works, because there are elegant, useful and very easily commonly available softwares for linear programming. In fact, in libraries like MATLAB, you can easily solve any of these optimization problems. However, for a student it is extremely important to know and understand how the algorithm works. In fact, in the classroom type of examples, you should be able to solve these problems with hand calculators, and therefore, it is important for us to know how the algorithm itself functions. So, we will start with, we will introduce over the today's class as well as the next class, we will discuss the simplex method, how it works. Before going into the actual functioning of the algorithm itself, let us look at the motivation for the simplex method. We will revisit the graphical solution, where we obtained a optimal solution. Just look at this, what did we achieve here? First, we formed the objective space or the feasible region. In the feasible region, the solution lies somewhere, we do not know where. So, somewhere the optimal solution lies, and then we started looking at how the z value increases. So, starting with the z value, we kept on increasing the z value, ensuring that it still lies within the feasible region, and we achieved that particular point beyond which the z can no further be increased without violating any of the constraints. And this we saw lies at a particular corner. So, the one observation that we made is that the optimal solution in this particular case was at a corner. If your z direction increases, changes, then still you are hitting at a corner. So, the solution will be at this corner and at this corner, and in this particular case it so happens that it will be all along this line. Let us say your z line was some other was increasing in some other direction. Let us look at, let us say z line was here, then it keeps on increasing in this direction, assume that it is increasing in this direction, then the optimal solution will be at this point. So, the observation that we are making is that the optimal solution lies at one of the corners of the feasible space. So, it can be either this corner, it can be this it can be this corner or this corner or this corner or this corner, etc. So, if we start the solution with some assumed value, let us say 0 0 was here, x 1 is equal to 0, x 2 is equal to 0 was here, which would have been z is equal to 0, and moved from this point to this point, 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 which means let us say that we enumerated all the corner points, the solutions at all the corner points, and then picked up the one that leads to the maximum. Then we are safe, because we know that the solution has to occur at one of the corner points of the feasible space. However, as the number of constraints increases, as the number of variables increases, the dimension of this feasible space will be quite large, and therefore, enumerating all the solutions at all the corner points will still be unwieldy. And therefore, we must have a mechanism by which, starting with a particular point, we must know whether I should go to this point or I should go to this point. In a multidimensional space, you imagine that you start with a particular point, and then you must be able to see whether I should go to a neighboring point in this direction, a neighboring point in this direction. This is what we achieve in the simplex algorithm. That means, we start with the feasible solution, we have identified the feasible region, we start with the feasible solution, and then instead of enumerating all possible feasible solutions, we will know, starting with the particular feasible solution, we will know in which direction the solution should proceed, so that we will hit the optimal solution in the least number of iterations. This is what we do. So, we will go to the motivation for the simplex problem now. Again, starting with a simple graphical solution. Let us say that you take a problem, maximize z is equal to 6 x 1 plus 8 x 2, subject to 5 x 1 plus 10 x 2 less than or equal to 60, 4 x 1 plus 4 x 2 less than or equal to 40, and x 1 and x 2 both are non-negative. If we solve this with graphical procedure, we get this feasible region. Let us say you just look at the constraints now, identify the feasible region. How did we identify? You draw this constraint 4 x 1 plus 4 x 2 is equal to 40, and then because it is less than this, you are looking at this direction. Similarly, 5 x 1 plus 10 x 2 is equal to 60. These are the two constraints. You draw this and identify the feasible region. Because x 1 is greater than or equal to 0, x 2 is greater than or equal to 0, this becomes the feasible region. So, you have the points O, A, C and D as the corner points of the feasible region. But there are also other points. You look at point B here, point E here. So, you have 6 points here on this diagram. Let us see what are all the features of these 6 points. You have two constraints, 4 x 1 plus 4 x 2 is equal to 40, 5 x 1 that is less than or equal to 40, and 5 x 1 plus 10 x 2 less than or equal to 60. These are the two constraints. Let us say the inequality constraint now, 5 x 1 plus 10 x 2 less than or equal to 60, I convert it into an equality constraint by adding a slack variable x 3 is equal to 60, and 4x1 plus 4x2 less than or equal to 40, I convert it into an equality constraint by adding another slack variable. Remember, this slack variable must be different from this slack variable. 4x1 plus 4x2 plus x4 is equal to 40. So, what happens in the process? You have 2 equations and 4 unknowns. So, m is less than n, and all your variables are greater than or equal to 0, which is the non-negativity condition. So, x3 and x4 are the slack variables. Let us look at what all these corner points and the points which are intersecting with the x1 and x2 axis correspond to. So, from this then we start developing start looking at the motivation for the simplex algorithm and introduce what are called as the basic solutions, basic feasible solutions, basic variables, non-basic variables and so on, and that leads to an algorithmic way of solving the LP problems. This we will continue the discussion in the next class. So, in today's class essentially what we did is we started with the graphical solution, we identified the feasible region, and then in the feasible region any point is a feasible solution, and therefore, you have infinitely many points which are all feasible. Out of these infinitely many points, we want to identify the optimal solution, for which what we did is we took a z line and then moved the z line parallel to itself in the direction in which it is increasing for an optimal maximization problem, and then identified that particular point beyond which the z cannot be increased any further without violating any of the at least one of the constraints, and that becomes the optimal solution. And we saw that this optimal solution in fact lies at one of the corners or coincides with one of the edges of the feasible space. And then we saw the special cases where you have multiple solutions, multiple optimal solutions. If you have 2 optimal solutions, you have infinite number of optimal solutions. Then there is a case of unbounded solutions where your set of constraints may be such that you will not have a bounded feasible region, and therefore, the z value can be increased for a maximization problem until infinity without violating any of the constraints. Then you may have infeasible solutions. In general, when you have unbounded solutions or infeasible solutions, the problem is ill formulated. So, you will have to look at the set of constraints. Then we just started looking at the general form of the LP and motivation for the simplex method. In the general form of the LP that we use in this course, we express the objective function as a maximization function and all the constraints as equality constraints, and all the variables must be non-negative. If you have a minimization objective function, you can convert it into maximization by taking negative of that function. If you have less than or equal to constraints, you add a slack variable to make it equality constraint. If you have a greater than or equal to constraint, you deduct a surplus variable. Both the slack variables and the surplus variables are non-negative, and convert them into equality constraints. If you have variables that are unrestricted in sign, you express those variables as difference of 2 variables, both of which are non-negative, to convert them into to use them as non-negative variables in the LP problem. So, we shall continue this discussion, and in the next class I will introduce the simplex method, or at least the motivation for the simplex method and how we identify basic variables, non-basic variables and so on. Thank you for your attention.